Welcome to AERO 1020, Theory of Flight, presentation number 8 on lift. In this presentation we'll be discussing lift theory, the lift vectors, center of pressure and distribution of lift, and the lift equation. An airfoil cannot generate lift unless it's moving through the air. So it's important for us to understand the properties of moving air, how air behaves when it's in motion. And the study of air in motion is known as aerodynamics. One way that we can study air in motion is with a wind tunnel, like the one pictured in this slide. Generating lift with an airfoil is unique to heavier than air aircraft, and it's defined as the net differential pressure between the upper and lower surfaces of an airfoil. It's important to remember that lift always acts perpendicular to the relative wind, and it always acts approximately perpendicular to the aircraft wing. The coefficient of lift is a measurement of lift that's generated by an airfoil, and it's determined for each wing design in wind tunnel testing. The coefficient of lift can also be described as the ratio of lift pressure to dynamic pressure. Here is a graph showing the coefficient of lift compared to the angle of attack. And as you can see in this graph, as the angle of attack is increased, so is the coefficient of lift, until it reaches what's known as the critical angle of attack. At the critical angle of attack, which is approximately 17 degrees nose up pitch, the wing or the airfoil will stop producing lift and go into an aerodynamic stall. So a stall is just the reduction in lift caused by the breakup of smooth air over the wing. So in other words, the smooth flow of air starts to break up, and this always happens at the critical angle of attack. The critical angle of attack is the angle of attack at which the air no longer flows smoothly over the upper surface of the wing, and that reduces the lift capability of the wing. There are several ways that a pilot can tell when an aircraft is about to stall, depending on the equipment on the aircraft. If the aircraft is equipped with an angle of attack indicator, then the angle of attack indicator can tell the pilot when the aircraft is close to that critical angle of attack. Another way is the stall buffet. Stall buffet is just a feeling of bumpiness just before the stall. Instead of the aircraft moving smoothly through the air, it starts to buffet or bounce. Some aircraft are equipped with what's called a stick shaker, and the stick shaker is designed to alert the pilot that it's close to an impending stall. Other aircraft are equipped with warning lights or warning horns to tell the pilot that it's close to a stall. And just being in a high nose attitude at a low airspeed will tell the pilot that the aircraft is close to that critical angle of attack and may be close to stall. Before we move on to discuss the lift theory, we should review the different types of pressure. Static pressure, remember, is the pressure of ambient air, or the pressure of still air. Dynamic air pressure is the pressure of air in motion, or kinetic energy of air. We can also look at it as the force necessary to bring a volume of air to a complete stop. And the formula for dynamic pressure is 1/2 rho times velocity squared, rho being air density. According to the conservation of energy, static pressure plus dynamic pressure equals total pressure, and total pressure is a constant. So if static pressure goes up, dynamic pressure must go down. If dynamic pressure goes up, static pressure must go down. Again, static pressure is the pressure of ambient or still air. Dynamic pressure is the pressure of moving air. And dynamic pressure plus static pressure equals total pressure. So who was Daniel Bernoulli? Well, Daniel Bernoulli was a Swiss mathematician and a physicist. His father, Johann, was a mathematician and an early developer of calculus. And Daniel had hoped to become a mathematician, but his father wanted him to be a physician. So Daniel agreed to study medicine if his father would teach him about math privately. Daniel went on to study fluid dynamics, or the study of fluid in motion. Bernoulli discovered that an increase in the velocity of a fluid will decrease the static pressure. Static pressure plus dynamic pressure equals total pressure. And remember, total pressure is a constant. If static pressure decreases, dynamic pressure must increase to keep total pressure constant. So P, which stands for static pressure, plus Q, which stands for dynamic pressure, equals H, which stands for total pressure. Bernoulli discovered that when you force a fluid through a narrow opening in a pipe, that the pressure actually decreases as the velocity of the fluid increases. So, according to Bernoulli's theorem, total pressure equals static pressure plus dynamic pressure, and total pressure is a constant. So when he studied fluid moving through a pipe, through a narrow opening in a pipe, and he discovered that the pressure would decrease as a result of the increase in velocity through the narrow opening. He also discovered one of the principles of lift. If you imagine that the top of this pipe is not there, and we draw an airfoil in this section of the pipe, we can see that the same principle occurs when air flows over an airfoil. The air, because of the shape of the airfoil, moves faster over the top of the airfoil than the air moving underneath the airfoil. As a result of that increased velocity over the top of the airfoil, the pressure is decreased. Higher pressure below, lower pressure above results in lift. Now, as demonstrated by the coefficient of lift graph that we saw earlier, the higher the angle of attack, the higher the coefficient of lift. So a higher angle of attack results in a higher coefficient of lift, which results in the wing producing more lift. A higher positive angle of attack also increases the effective top surface of the wing, and it's increased due to a change in the stagnation point. The stagnation point is the dividing point at the leading edge of the airfoil between the upper and lower flow of air. So this is the point at the leading edge of the wing where the air either separates and goes over the wing or goes under the wing. And the stagnation point can also stop air particles from moving altogether. So some air particles in the stagnation point come to a complete stop. Now, in addition to the theory of lift that's related to the differential pressure between the upper surface and the lower surface of the wing, created by the increased velocity of air flowing over the wing, there's another view of lift related to Newton's third law. For every action, there's an equal and opposite reaction. Lift occurs when a moving gas, or air, is turned by a solid object, the wing in this case, and deflected down. That downward deflection results in an opposite reaction upward, And that's related again to Newton's third law. For our reaction, there's an equal and opposite reaction. So in addition to upwash, as the wind flows over and under the wing, there's also downwash. That downwash is what creates the opposite reaction upward. So in addition to differential pressure, we also have Newton's third law acting on the wing to produce lift. So the action of the airfoil moving through the air gives the air a downward push. That downward push results in an opposite reaction up, and that contributes to the lift created by the wing. As you can see in this illustration, lift is created as the air hits the leading edge of the wing and is deflected down. That's called downwash. How can we represent lift graphically? Well, lift not only has magnitude, but it has direction. So we can use pressure vector arrows to represent lift. So lift can be graphically represented by a vector on paper with an arrow. The direction of the arrow represents the direction of the force. The length of the arrow represents the magnitude, or the amount of force applied. So again, the vector arrows represent the direction of the force as well as the magnitude of the force. In this illustration, we see an airfoil at a -3 degree angle of attack. And as you can see, the lift vector arrows are longer on the underside of the airfoil than above the airfoil. So this airfoil is not generating a great amount of lift. In this illustration, you see an airfoil at a +3 degree angle of attack. And as you can see, the lift vector arrows are longer above the airfoil than below the airfoil. So at a +3 degree angle of attack, this airfoil is generating positive lift. And just as we saw in the coefficient of lift graph, as the angle of attack is increased, so is the amount of lift. In this illustration, this airfoil is at a 19 degree angle of attack. So you can see that the lift vector arrows are much longer above the airfoil than below. Notice that most of the lift is generated close to the leading edge of the wing at a high angle of attack. The largest pressure variations occur within the first 25% of the airfoil, closer to the leading edge. So most of the lift is developed close to the leading edge of the wing. An important term to remember is the center of pressure. The center of pressure is the point on the airfoil at which the lift is concentrated. And as you can see in this illustration, as the angle of attack of the airfoil is increased, the center of pressure actually moves forward, closer to the leading edge of the wing, if the airfoil is asymmetrical. Aerodynamics defines the total lift of a wing as the force acting through the center of pressure, or the single point on the airfoil called the center of pressure. The center of pressure can be subdivided into an upper surface center of pressure as well as a lower surface center of pressure. Now, because the center of pressure on the upper surface of the wing is behind the center of pressure on the lower surface of the wing, there is a natural nose-down pitching moment. The airfoil tends to pitch forward because of the different locations of the center of pressure on the upper surface versus the lower surface of the wing. So let's summarize the pressures on the airfoil. The pressure distribution varies with the angle of attack. The pressure difference between the upper and lower surface of the airfoil is called lift. The largest variation of pressure occurs in the first 25% of the airfoil, closer to the leading edge of the wing. So most of the lift is developed within the first 25% of the airfoil. This tells us why icing can be a problem. If ice develops on the leading edge of the wing, then you could disturb that smooth air flow over the airfoil, and the result is a significant loss in lift. Also, because the center of pressure on the upper surface of the wing is located behind the center of pressure on the lower surface of the wing, that can result in a nose-down pitching moment on the airfoil. In this illustration, we can see the effect of ice on the leading edge of the wing. You can have clear ice, rime ice, or mixed ice, which significantly changes the shape of the leading edge of the wing, and that can disturb the smooth flow of air over the wing, which can disturb lift. So finally, we come to the lift equation. The lift equation is simply lift equals the coefficient of lift times 1/2 rho, and rho is the density of air, times velocity squared times the surface area of the wing. Lift is usually measured in pounds, and the coefficient of lift, remember, is specific to a particular wing and associated with a particular angle of attack. So as you remember in the coefficient of lift graph, the greater the angle of attack, the greater the coefficient of lift. 1/2 rho times velocity squared is Bernoulli's equation for dynamic air pressure. That's a very important thing to remember for the test. The symbol rho again signifies air density, and V stands for velocity. So notice that velocity is squared in the equation. So that what that tells you is velocity has a huge effect on lift. Lift increases exponentially as velocity increases. And the surface area of the wing is represented by S. So the larger the surface area of the wing, the more lift the wing creates. So again, here is the coefficient of lift graph, and as you can see, as the angle of attack increases up to the critical angle of attack, the coefficient of lift increases. As the coefficient of lift increases, so does the amount of lift created by the airfoil. So notice in the lift equation that we can change lift by changing the angle of attack according to the coefficient of lift graph. How else can we change lift according to the lift equation? Well, again, we can change the velocity. We can increase our speed or decrease our speed. And by changing the speed, we can change lift exponentially. We can also use flaps to change the wing surface of our wing. By extending flaps, we actually increase the wing surface of the wing, and by increasing the wing surface, we increase lift. So those are the important points to remember about the lift equation. That's the end of presentation 8 on lift. The next presentation, 9, will cover the boundary layer.